because I think people, the rigor of people is kind of down to a trickle. So Emanuele Viola is our next speaker, and go ahead, the next hour is all yours.
Hi. Yeah, thank you very much for the invitation to this workshop and for the opportunity of speaking here. I'm very much enjoying it. I'm sorry that I cannot be there in person. So I have a couple of quick announcements. First of all, 15 years ago, I wrote a survey on correlation bounds for polynomials. I've just revised it just a few months ago. So if you want to have kind of like an organic, uniform viewpoint rendering of this material, maybe you can check it. It's on my webpage. The second thing is that I'm currently spending time writing a book. Computational complexity is being serialized on my blog, and any comment would be very welcome. Okay. So this is a possible view of complexity theory. It looks like a pyramid. At the top, we have, the P versus NP problem, and at the base of the pyramid, you have a bunch of, very interesting but somewhat specialized problems like circuits, involving circuits, communication, rigidity, polynomials, and so forth. And go ahead. No.
I have a editorial. P not equal NP is not the top of the pyramid. It's down near the base.
Okay. Okay.
And after that, we start doing computation complexity after we show P not equal NP.
Yeah. Thank you, Russ. Yes. Yes. Yeah. Okay. Okay. So I'm going to go ahead. Yeah, I agree. I'm going to propose a different view. That the pyramid is maybe upside down. So P versus NP is still at the top. Okay. There's going to be something more after that, but for now, I'm just going to focus on this. And actually, there aren't really that many problems here. There's maybe only a few problems, and maybe only a handful at the tip and at the base of the pyramid that we really have to understand to make progress. And a good question is what goes in here. Okay. So to answer this question, I'm going to now consider a few different problems, well-known frontier problems in complexity. Okay. So one problem is they're proving circuit over bounds. Okay, I'm not gonna define it more formally now. Another problem is to exhibit matrices which are rigid. This is something which was proposed by Valiant in the 70s, and it means to come up with matrices which are far in Hamming distance from low-rank matrices. Okay, so matrix which you have to change many entries to get a low-rank matrix. Okay. Another question is correlation bounds for polynomials. So this means exhibiting functions which are very hard to compute on average. They don't correlate with polynomials. I'm going to define formally some of these boxes in just a bit, but for now I'm focusing on the big picture. Okay, and another question is multi-party communication complexity. This, especially in the number on forehead model, this fascinating setting by Chandra, Furst, and Lipton in the 80s. And here we are stuck at the log n players, as is well known. So these are all long-standing problems, and I'm going to put some arrows now. So I'm going to put an arrow from A to B if progress on A requires progress on B. Okay, so one arrow is here. It's from circuit over bounds to correlation bounds for polynomials. So what does this mean? If you want to prove strong circuit over bounds, you actually have to prove correlation bounds for polynomials. Why is that? So I'm just going to say it in words. Right, because if you have a function f, and for every distribution, so here by correlation bounds I mean for any distribution. So if for every distribution I can exhibit a polynomial which has some good enough correlation, then I can use the standard min-max, LP duality, Ham-Banach, how you want to call it, argument to compute this function in the worst case, okay, by some majority of polynomials, which you can write as a small circuit. Okay, depending on the parameters, this circuit could have quasi-polynomial size, or you can be more precise about the sparsity of the polynomial. I'm not going to get into that now. Let's just say quasi-polynomial size circuit. Okay, so if you want to prove super quasi-polynomial size circuit lower bounds, even for depth 3, then you gotta prove this correlation bounds for polynomials. I'm going to define exactly the correlation bounds in just a few slides. This is well known. Perhaps something which is maybe a little bit less well known is that even matrix rigidity implies correlation bounds for polynomials. And here the catch is that even if you want a constant relative error in matrix rigidity, you must prove a very strong average case harden for polynomials. So you go to, like, you know, constant error here to like half minus little one error here. So you can sort of like boost the error. So in the setting of Valiant, for example, in which you just want some constant error, you must prove first very strong correlation bounds for polynomials. And you may have guessed now that you also have an error from here. This also is maybe not too well known. And here again, the catch is that even if you want to prove a worst case lower bounds for multi-party communication complexity for more than log n players, okay? So breaking this long-standing log n barrier for multi-party communication complexity in the number for a protocol, even in the worst case, you must prove a correlation bound, like average case harder for polynomials. Okay, and there's more. So I'm going to discuss later one more error, which is more recent. And recently there's been some proposals of some Fourier conjectures for polynomials, and it was not clear that these things require the correlation bounds, but you know, it was shown that even those require correlation bounds. And I will say more about this last error. Okay, so given this, I'm going to propose this picture here. Okay, that maybe these problems on polynomials are worth a little bit of effort. And you know, I don't know that they are necessary for every long-standing problem in complexity theory, of course, but I don't know of another problem, and maybe you know, and I'd be curious to hear of that. I don't know of another problem that, you know, it's required for such a variety of long-standing questions in complexity theory. Okay. So I'm going to now formally define these correlation bounds for polynomials. And again, if you want to have, you know, some background, you can look at my survey. So just to be precise now, so the challenge here is to exhibit a function, let's say on n bits, a Boolean function, and some distribution x on the input, such that for every polynomial p of degree d, okay, the correlation between f and p is small. So the correlation is just, it's a fancy name for the probability that f of x is equal to p of x, where x is drawn from our distribution. Okay, and it should be at most half plus epsilon. You can always get half just by random guessing, and this is half plus epsilon. So what do we know? There's two very well-known bounds that I'm going to discuss again for background. So in the 80s, Rasborough and Smolensky proved in particular this bound that the root is actually from Smolensky's paper, but Rasborough proved something similar for other symmetric functions.
Manuel,
Yeah.
I think I know the answer, but I just want to make it spelled out. You're talking about polynomials mod 2,
Yes,
right?
so, yes, sorry, I should, yeah. The polynomials mod 2, so yeah, mod 2. Yeah. Thank you, Russell. Yeah, so just think, actually, you can phrase these things also for mod 2. And in fact, by the way, Russell, I think a question that I like very much, this thing here is surprisingly is even open for a real values polynomials, where any non-Boolean output counts in your favor as a mistake. Okay, so even giving a polynomial, even giving a function that cannot be does not have this correlation with the real value polynomials, if you output 17, it counts as a mistake. Even this is open. And a candidate for that is parity, but we don't know how to prove it. But for now, so after this parenthetical remark, for now you can think of mod2 polynomials. The connections from before are for mod2 polynomials, but this question here is even open for real. I think it's really, I think it's an interesting question. It's kind of like it's the polynomial analog of the rigidity question, because the rigidity question is typically over real, so you can think of it as the polynomial analog of the rigidity question. But okay, so for now, let's just think of mod2. So it's known that for the majority function, you can pick a uniform distribution, and you have this bound of the error would be d over root n. Okay, so this is like great. It handles very large degrees, like polynomial degrees, right? But the error is not that good, right? It's just 1 over root n at best. On the other hand of the spectrum, you know, this fascinating work by Barbine and Zagati, which introduced this iterated Cauchy-Schwarz technique in the field that they proved for different functions, like the generalized inner product or the mod3 functions, that you can get error which is exponentially small in n over 2d. So this is like fantastic. When d is tiny, you get exponentially small, and it does nothing when d is like log n. Okay. So in particular, one setting which is covered by neither result is this epsilon 1 over root n. Give me error 1 over root n, and for degree log n. Okay, this thing is not work. Like this thing doesn't give you a good enough error. This thing does not give you a good enough. And interestingly, this setting here, this one here, is formally required for progress on any of the problems in the previous slide. So if I go back here, so you know, variance problems, the more than log, like polylog players, the multi-party communication complexity, the Fourier conjectures, quasi-positive bounds, they all require you to solve this. Yeah, so that's the state of affairs. Any questions up to now? Okay, so this was introduction. Again, now I'm going to mention a couple of recent results on correlation bounds, and yeah, and then we'll go to some pseudorandom generators and some more recent results. So the one thing that I want to start with is this nice work by these people here, appeared just a couple of years ago. They defined a notion of local correlation. Okay, so if you have a function, okay, now it's not working. If you have a function, and if you have a subset of the variables, you look at what happens when you pick a random the values outside of the set S of variables, and you look at the variance of what's left, okay, or the variance just over the variables in S. Okay, and they prove this nice thing that if you have a polynomial f, this local correlation is small, and you can find for a set S of variables which is of size only, quote unquote only, of size exponential in the degree. Okay, so this is like nice when degree is small. When the degree is small, they use this to obtain a new correlation bounds, which we don't know how to prove otherwise, as far as I know. But it doesn't.
Sorry.
Yeah. Oh, yeah.
Oh, just a small question. It's the square inside the bracket instead of out.
This is work with Ivanov as a PhD student. Pavlovich was at the time an undergraduate. He's now a PhD student as well. We give a counterexample to this conjecture. And in fact, we roll out even a weak form. They actually conjecture something much stronger, but we roll out like even a weak form. We show that what they prove is the best possible, essentially. And the proof is, you know, I can sketch it now. So you can start with the tribes DNF. this is, it's a standard extremal example in the analysis of Boolean functions. Like it's an order of n's. Okay, it has interesting properties, and it can be shown that this thread function has some good properties, kind of extractor-like properties on one side. So in particular, if you set the variables outside of S, and S can be as large as about n over log n, then that's enough to force the function to be 1 with constant probability. Okay, so just setting the values, so you have like a pretty large set S. If you set the variable outside of S uniformly, that's enough to force the function to be constant, to be 1 with constant probability. Okay, and then if you think about it, the local correlation has to be large, because the expectation of the tribes is about 0, is a balanced function. So this expectation over XS here has to compensate for this constant here. So it has to be pretty different from 0. So you have large local correlation. And okay, it's a DNF, it's not a polynomial, but the thing is that you can approximate it by low degree polynomial, kind of like the Rasborov way. And you can prove that this approximation actually would preserve this large local correlation. So you can approximate it by a log n degree polynomial, and you still have large local correlation. So this is a counterexample. Well, Tisho, any questions? Yeah. So I know this maybe should make us think that maybe we need some new approaches. And in fact, there's even some barriers for proving correlation bounds. There's like a nice work about non-classical polynomials being a barrier, and so this is a barrier which is specific to polynomials. So we should maybe think of some other approaches. So in this work, we propose one such approach. So we make a conjecture which is maybe bold, but it's plausible as far as I know. So we conjecture that if you look at functions like mod3, the polynomials mod2, which maximize the correlation, are symmetric. When I say maximize the correlation, I don't mean almost optimal. I mean exactly. So right here, exactly. So these are the exact maximizer. You cannot do anything better than that. This is somewhat strange, perhaps because in other settings, symmetric polynomials are known to not be optimal. But in this setting, which would be important, we conjecture that they are. Okay, and if it was the case, this would imply some dream correlation bounds, because it's known that symmetric polynomials have very small correlation with mod3 functions. I'm going to make a couple of comments on this conjecture. So one is that this thing actually seems to bypass these barriers that I just mentioned. In particular, you wouldn't need to distinguish between classical and non-classical polynomials, as far as we know. So the barrier that I mentioned does not seem to apply. And also, we actually have, the conjecture is not just for mod3, and our results are not just for mod3, but are more generally for these phase functions. So you can take any complex number z, and you can raise it to the sum of the xi's. So z just any complex number on the unit circle. So mod3 is a special case of this, but we conjecture this for any such function, and we actually we prove it in the case of degree 2. So a main result in this work is that we can prove this conjecture for degree 2 polynomials. So the exact maximizers of the correlation with mod 3, in fact, with any function of this type for any z, so even mod 5 and mod p, anything else are quadratic, are symmetric. And this is, is done by a technique which doesn't seem to have appeared earlier. So we kind of like write down the correlation in terms of derivatives, and then we kind of like open one bit of the derivative at the time, and each bit that you open, each bit that you fix, we connect it to the corresponding derivative for the symmetric case. So we can like slowly match the symmetric derivatives to the derivatives of any quadratic polynomial. So I'm not gonna say more about this proof because I want to discuss other things. But the case of degree 3 is open. It's only known for some special classes of degree 3. I think it would be nice to prove it for a degree 3, but it's not known. Any questions? Okay. Okay, so I want to move to a little bit other things. I want to talk about pseudorandom generators and some other results. So, okay. So pseudorandom generators, you all know what they are, so I'm not going to define them again. I want to make a couple of comments that they're known to be equivalent to correlation bounds if the error is small. Okay, so if you give me a PRG which has very small error epsilon, this implies a correlation bounds with about the same epsilon. And the way around is known if the correlation bound is proved under the uniform distribution. This is via Nissan's famous design construction. If I give you a correlation bound with very small error for the uniform distribution, you can construct a PRG. I don't know what happens for large errors. So conceivably, you can have a generator which has constant error and being completely unrelated to correlation bounds for small error. I only know of the one work which connects the two, but it's only for a special class of generators. Like yeah, so I think it's interesting question to try to relate what happens like PRGs with constant error and correlation bounds for small error, but I don't know how to do it. Okay, so the state of the art for PRGs for low degree polynomials is in this series of works, and the paradigm is in this work with Andrei Bogdanov that says that if you want to full degree the polynomials, the way that you can do it is you take d independent copies of generators for degree 1 polynomials and you just use sum them together. Okay, so it's a very simple paradigm. You just take d copies of generators for degree 1 and you sum them. And this actually can be analyzed for degree a small constant times log n, but beyond that is unknown. So it's conceivable that this thing works for any degree, like degree n to the epsilon, and it can never be, a breakthrough result, but nobody can prove it or give a counterexample. And I'm going to discuss this thing later because of some recent work. But now I'm going to talk about these Fourier conjectures, which I mentioned earlier. So to try to improve this for problems and also in other settings, there's been some new paradigms being proposed that are called the polarizing random walks. And that basically it's a way to construct PRGs, pseudorandom generators from Fourier bounds. So in an effort to get better results for polynomials, some specific Fourier conjectures were put forth for the Fourier spectrum of polynomials. So in particular, it was conjectured that if you have a polynomial P of degree D, if you sum the Fourier coefficients of size 2, then you get a bound which is only quadratic in the degree of the polynomial. Okay, while actually for other functions like majority can get much bigger. It can be like root n or something. More generally, it was conjectured that if you look at the sum of the Fourier coefficients of size k, you get this bound here. The second bound also was also quoted by Glee, who's very strong as a PhD student of mine. Is currently on the job market, so you should interview him and hire him if you can. Okay, so these things were proposed, and so a theorem that we proved is that this conjecture, in fact, even weaker ones, they imply collision bounds which solve the problem in the previous slide. They particularly beat Rasborough-Smolensky global bounds, and the functions that would be hard for polynomials are some variants of majority. They are kind of like polynomial threshold functions. Okay, so even proving these things, so it was not clear at the beginning that you would need correlation bounds for this approach. Also, some of these things only gave PRGs with a constant error, so it was not clear that they implied correlation bounds via the previous connections, but via this new connection, you can show that they still require correlation bounds. Any questions on this? So I'm not going to say much about this proof because I want to talk about other things, but it's not hard. It's like half a page. But because of this, we gave some more thought about correlation bounds for majority. So I want to discuss this a little bit. So, one approach now to refuting these conjectures would be to just give correlation upper bounds for these things. Like maybe these things are actually easy to correlate with, and then the conjectures would be false. So we tried to do that. So we aimed to resolve these conjectures, but we didn't manage. Still, we discovered just some things that I want to tell you about. So one thing that I want to emphasize, which I think is a nice problem, is that the correlation with majority is open. So we don't know. It was somewhat surprising to me. It was not clear in my head, but this thing is not known. So Smolensky proved this bound, which I mentioned earlier, of d over root n, fantastic for majority, and this thing can be shown to be tight, best possible bound, under the uniform distribution. Okay, you have polynomials which have this correlation with majority under the uniform distribution. Okay, it's not immediate, but you can cook up polynomials that do that. But it's only under the uniform. Now, what happens under what is like a worst case distribution? How bad can this thing be? Does anyone have any guess?
The slice?
What's that? Yeah, so that would be the distribution. Do you think what bound do you think we can have under every distribution? What would be any guesses? Actually, I don't know. I mean, it's still open, but some new bounds are being proved.
I think maybe it's still d over root n.
It's not. Yeah.
Not.
See? It's not. So this next claim does not refute what you said, but the one at the bottom does. So it can be shown that you can have polynomials which have correlation quadratic in this, so d square over n, under every distribution. Okay, so this is a construction of polynomials which have correlation square of this. This is kind of like weaker in terms of bounds, but it works under every distribution. For every distribution, I can give you a polynomial which has correlation d square over n, which is the square of Smolensky bound. And I conjecture that that this thing is tight. This I think is the tight bound for polynomials. And I don't know how to prove it, but it can be shown in the simple case of degree 1. Okay, this seems like simple, like it's just degree 1, it's just linear polynomials. But so it looks trivial, and maybe it is, but observe that this already requires you to go beyond the uniform distributions, right? Because for uniform distribution, the right bound would be 1 over n. Okay, and here actually you get 1 over n. You get like a stronger bound here for degree 1. So this actually, so what Russell was saying, the over n is not correct, because for d1 you get 1 over n. Actually, the bound is 1 over n. And again, yes, the distribution here, the hard distribution here would be like, you get 2 Hamming weights, 2 slices, and you can prove that it gives you this bound. So it seems realistic that for larger degrees you can get a bit more slices. Maybe you get these slices, okay, and you get this bound here, but it gets kind of technical, and I was not able to make much progress. But I think it's possible to do it, like maybe at least for constant degree. I think it's a nice question. I hope that I can interest some of you. It seems like it really, to me, like a basic question about majority and polynomials, but that's the state of affairs. Any questions? Okay, so that's the thing. Okay, so now I want to talk about a recent result about a new approach to construct pseudorandom generators using invariant theory and other things. Yeah, so let's move to that, and let's see where we get. So I didn't define pseudorandom generators until now. I'm going to define them now, because we're going to have to play with the field size. So I want to make sure that everybody is on board with different fields. So just to be precise, for a minute, so pseudorandom generator, now it's a map from S bits. Okay, so the seed length is S to a tuple of n field elements, and I'm working over a generic finite field F. Okay, and I claim that I say that this thing fools degree polynomials in n variables if the statistical distance between the output distribution of the polynomial over uniform inputs is close to the statistical distance between the P of U, right, is and the output distribution of the polynomial when you plug the output of the generator is small. Okay, so these are distributions over F, the field. So they're not just bits. I cannot just look at what's the probability of outputting one. I have to look at the whole distribution, and the fields are going to be large now. So I want to have that the statistical distance is small. We're going to be able to achieve that. You could think of weaker notions, like maybe like hitting the zeros, but this is we're going to be able to achieve this. Okay, so this is our notion, and there's actually 2 lines of works on this. And one is the case of small fields, and everything that I was mentioning until now, essentially, except for a small remark, is for small fields like 0, 1, okay, like mod2. And this started, with this, landmark paper by Naur and Naur in the 90s, which they do with this small bias generators, which does it for degree 1, which has, like a myriad applications. And then the case of large degree, as I mentioned earlier, is this work with Bogdanov. And we have this paradigm which we introduced, that if you want to full degree D, you take D copies of the generator for degree 1, and you just sum. Okay, so it's a very simple construction. and it can be analyzed, and the seed length is log n plus exponential in d. So this, as I mentioned earlier, doesn't do anything for degree larger than log n, and it's an open problem. Like there could be a counterexample. I spent like a lot of time trying to come up with a counterexample for large D, and I failed. So maybe there isn't a counterexample. I don't know. I would be very happy to know that. And then there's actually another line of work which predates this paradigm, which is the case of large fields. And here there is a very nice paper by Bogdan or by Andrei, whom we just saw in the previous talk, which goes to a completely different route, and it reduces the question of constructing generators to a hitting set. So in which you don't want to, you just want to hit a polynomial. Okay, so I'm not going to discuss this in detail, but then after this, and motivated by this, there was like a series of constructions of hitting sets for polynomials, which now are known with optimal parameters. So now we know that the best possible hitting set that you might want to plug in this specific connection. And if you use them, you get a seed length for generators of this type. It's a power of d to the 4 log n plus log the field size. Okay, if the field is large enough. Okay, so a drawback of these things is that the dependence of d in the seed length, is not terribly good. It's d to the power 4, while the right dependence is just d. Okay, and in fact, it can be shown, and we argue in our work later, that this approach cannot give you seed length even less than d square. Okay, there's like a bottleneck in this reduction that prevents you from getting like close to d. But the more interesting, I think, these two approaches were completely different. Like this, you sum degree 1 things, and you have this hitting set. It's a completely different approaches. And yeah. So go ahead.
A very silly question on the small field construction. If you only sum up D generators, why do you need 2 to DC length? Is it because of the error?
Yeah.
Thanks.
Yes. So yeah, so the error, you go from error epsilon to error square root epsilon for every time that you apply this. So that's the problem. And actually, a fantastic question, in my opinion. Sorry, I'm totally biased, so I shouldn't say fantastic, but anyway, something that I spent a lot of time is this, right? I mean, let's just say that you go from degree 1 to degree 2. Okay, so all that we know how to do is this loss here, the square root loss. I mean, is this inherent to full degree 2 polynomial? Like, forget going to degree like log n or beyond. Just from degree 1 to degree 2. Can you save this square root? I would really love to see an answer to the question, but it's not known. Okay, so these two lines have followed different paradigms, and so I want to talk now about this work with Dirksen. He's a mathematician at Northeastern. So we were able actually to analyze this Bogdanov-Viola paradigm for large degrees. So this is good, it's what we want, but only, of course, the catch is that we can analyze it for over large fields. Okay, but we can analyze what happens when you sum generators for degree 1, even over large degrees, if the field is large enough. And using this, we can get new generators over large fields. Okay, so in particular, we are able to get optimal seed length, which is a d log n plus log the size of the field. This is the optimal dependence up to constant in front if the field is large enough. So the field has to have, size d to the power 4 times some power in n, the number of variables. Okay. If you want to reduce the dependence on n, you can make it power of the log of n. So that's much better, and you get almost optimal. You get like nearly optimal. So you're gonna have some logs here hidden in this O tilde. And now if you're really stingy with your n, you want like no dependence on n, then we can match the previous best that we had in terms of seed length, the ones that comes from the Bogdanov thing, but we only require field size d to the power 4, while the previous work had d to the power 6. Okay, now maybe not, I mean, who cares? It's just 4, 6, 3, 4, 5. Who cares? Well, actually, there is a point that 4 is the right constant because it's the best possible that you can get with veil bound. Okay, so all this works with large degrees and large field. They all rely on veil bound from algebraic geometry. Bogdanov required, we required it, and that bound is only applicable when the field size is a fourth power of d. Okay, so the bound is the field has to be quadratic in the genus of the surface, and the surface of a polynomial of degree d has genus which is quadratic in the degree. So you get a power 4. So if you want to improve this power 4, you have to go beyond the veil bound, which is seems like a challenge. So yeah, this is like the best that you can get if you want to use a veil bound. Okay, so I'm kind of happy because I asked for 15 more minutes, and I think actually I'm going to use it. I was worried of like just using a bit of less time, but yeah. So I want to try to give you some ideas of how this proof works, because you use some ideas, some concepts which were not used in this area before, so maybe they can be used for something else. Okay, so okay, so now is there any question on the statements before we get into the proof? Okay. Okay, so I want to give you an overview of the proof. I want to expose you to some concepts which I didn't know about, and I felt like that I was learning something when I was doing this. So I think maybe it's good to review them. So one notion that we use is that of decomposability of polynomials. So and this so I'm going to say that the polynomial G over some field is decomposable if what? If you can write G as the composition of a univariate polynomial C with a multivariate polynomial H for some univariate C of degree bigger than 2. Okay, so for example, okay, if I have, if my G is, the sum of the xi's square, okay, this thing is obviously decomposable. This is maybe the simplest
Emanuele,
possible.
we can't actually see what you're writing.
Oh,
that's where your face is.
Oh, okay. Can I write on the left?
Down below.
Can I hear?
The upper left corner should be fine. Yeah, thank you.
Okay, no, thank you for telling me. I didn't know that my face. Okay, so if G is the sum of the xi's square, right, this is maybe the simplest possible example. This thing is decomposable, so I can take C, my univariate polynomial, just x squared, okay, and H would be just the sum of the xi's. Okay, so this implies that the G is decomposable. Okay, you can think of other examples, of course, but this is simple. So C is a univariate polynomial. Okay, so you decompose as this. And a lemma that we prove by putting together some results in algebraic geometry is one here, which is important for this work. that if you have any polynomial G which is indecomposable, that cannot be decomposed, so it's you know, it's a rigid thing that cannot be decomposed, it's indecomposable, then in fact the output distribution of G over uniform is close to uniform, right? In this example here with the square, the distribution will not be uniform, right? Because it's just going to be a square, so it's very different from uniform distribution, just uniform over the squares. If the field that's like, you know, it's prime, it will just be squares. So if the polynomial is not decomposable, then you have the guarantee, somewhat magically, that if you plug uniform values for the variables and you see what polynomial spits out, it's going to be close to uniform. Okay, so this looks powerful. And so the main lemma that we show is not this, is this one that comes here. The main lemma that we show is a construction of polynomials f1, f2, fn, which has some nice properties. The main important properties for us is that they preserve indecomposability. Okay, so if you have a polynomial h and you plug these f's for the variables, if this composed thing is decomposable, then in fact even the original polynomial in the x's was decomposable. Okay, so they preserve indecomposability. Okay, and the polynomials also needs to have, you know, few variables and have low degree. Okay, because you're going to pay all these things in the seed length. But the key property is that they preserve indecomposability. And okay, so once this, now I can give you the generator. I can tell you. So let me sketch the generator. So my generator would just be the f's. Okay, so you take a bunch of random values for the variables and you feed them into the f's. So that, you know, it's f1, f2, fn of this thing. Okay, so the first output variable for the generator is just f1 of the u. The second will be f2 of the u, and so on. So you have n variables that you compute from a small seed u, which maybe is only a handful of variables. So let me now sketch you how you put all these things together to prove that this thing fools a polynomial. So let's say that you want to fool some polynomial g. Okay, so you have some g, you want to fool it with these f's. Okay, so how do I accomplish that? So my first step is that I'm going to write g as a c composed with h, where c now is a univariate polynomial of maximum degree. Okay, so I pick a univariate polynomial of maximum degree and I write g as ch. And a critical observation is that this h here is indecomposable. This h here is indecomposable. Can someone tell me why that's the case? Okay. Can someone follow this? What would happen if you could decompose h? What's that?
Max degree. Yeah.
Exactly. Thank you. Right. So if h could be decomposed further, then in fact c would not be of maximum degree. Right. So I could like compose a piece of h in c. So because I pick c of maximum degree, this h here is indecomposable. But now I can apply this lemma here. So if you think of gu, I can write g as chu, right? This is just just writing. But because h is indecomposable by the lemma, h of u has the same distribution as just u. It's just a uniform. Okay, this is like a key step. Okay, and because the f's in decomposability, even the h of the f's is indecomposable. So I can also write u as h of the f's, right? Because of this lemma again. Okay, and you know, c of the h of the f's is just my g on my generator, right? And so that's what I wanted to show. The g of the f's has the same distribution as g of u. Okay, this u here is on much fewer variables than this u here. This what I'm getting in seed. That's
Another small question.
yeah. Go ahead.
Where in the proof do you use f is large? I guess both the lemma and the main lemma.
Yeah, so in actually in both places. So no. So not to comment that if I mean that actually this thing we give several versions of this, and in fact we can prove this even over F2. So we can have construction.
Cool.
Yeah, if we just want to preserve this, it only shows up here. The large F is only for this step here. This is where I use a field bound.
And I guess the distance between GU and the uniform distribution depends on the field size.
Yeah, I mean, here you cannot prove anything if the field is small. I mean, yeah, you cannot prove. I mean, yeah, you will have like a distance like 1 or something if the field is small.
Thanks.
So, yeah.
Thanks.
Cool. Okay. No, thank you. Okay, so I need to define the f's. So I want to define these f's. Okay. In fact, the definition is simple. So I want to give you like 1 minute definition. So you can start with yeah, you can start with any collection of monomials in some n variables of degree k. So just forget everything. You have m variables, and you just look at all possible monomials of some degree in those variables. Okay, and then just like in the paradigm from before, if you want a full degree D polynomials, you're going to take D copies of the variables. So if you have a variable x, I'm going to have variables x1, variables copy x2, and so on. So in the superscript, I have which copy of the variable. So you can think of the variables as being in a matrix. You have D copies, and my fi, which was the ith output of my generator, it's you take the ith monomial and you sum it over any possible copy of the variable. Okay, so if your monomial was like xy, then f would be xy with respect to the first copy plus xy with respect to the second copy, and so on. Okay, so you take any monomial and you just sum it over the copies, and this is like it's an algebraic version of this paradigm of summing over different copies. Also because you don't have to take monomials. You can take, in fact, you can start with any mice which full degree 1 polynomials. You can prove that. You take copies of that, and this would be a good enough definition of the fi. Okay, so okay, so I want to spend just a minute where the invariant theory shows up, because I think this shows how you exploit this this fact that you take copies. So our goal is to show that these FIs preserve in decomposability. So I want to show that if you have a polynomial g, little g, and you plug my FIs, which I defined earlier, that just the sum of monomials over copies of variables, if you could decompose this, which means I can write it as a C composed with some H in the X's, okay? Then in fact, even the original polynomial G just in the X's can be decomposed as something else, C of little h, okay? This is my goal. And also that this FI is preserved in decomposability. And I just want to flash the key steps of this to show you where the invariant theory comes up, because it seems that it could be useful in this area. So so the critical observation is that this polynomial here, little g composed with the f, is invariant under permuting the copies of the variables. This is for trivial reasons, because my FIs, if I permute the copies, they will not change because they are defined as the sum of the copies. And so even this polynomial here, the composition of G with the F's is invariant. So if you permute the copies of the variables, you don't change the polynomial. So using this, you can show that if you could decompose it, even this polynomial here would be invariant under permuting the copies. This is like a step. And it can also be shown that these FIs that I pick are a basis for the invariant polynomials. So because my H is invariant, I can write H as a polynomial of these Fs. Okay, so these polynomials in which you take copies, they can express any possible invariant polynomial. They're a basis for the invariant ring of polynomials. Okay, so you can write H because H is invariant. H in the X is invariant, so I can write it as a polynomial, a little h in the Fs. And from this, you can conclude, using the structure of the Fs, that G itself can be decomposed. Okay, I'm not gonna say more because I think it's getting late. But the key thing that I want to emphasize is that because of the structure of the generator, it's invariant in the permutation. So if you can decompose into CH, you can also write H. Also, H is invariant, and you can write it as a polynomial in the Fs, and then you can conclude that the original H, the original G was also invariant. Okay, so I'm going to move on unless the question. Just want to mention, like, super quickly, we actually give several different analyses of this idea. The simplest one is not hard at all. It's just, I don't know, maybe two pages. It's fairly elementary math. I think it's fairly accessible, like even to me. There's not too much going on. It doesn't quite give the best possible parameters, but it still gives some pretty good parameters. The most advanced version, it's complicated, but using that, we can get the best possible parameters. And we can also, as the previous question, we can get it to work over any field. So if you just want to preserve in decomposability, you can also do it over F2. So the only constraint on the field size now is from veil bound. Okay, last comment on this all this stuff that I said actually doesn't quite give the optimal dependence, because if you think about that, I'm still plugging field values for the variables of the polynomial, so it will still give a multiplicative dependence on the field size, like no matter what I do, because you have field elements. But in fact, the right dependence is additive. And to achieve this, actually, you need one more step. We combine this stuff that I just discussed with a variant of Bogdanov generator based on the heating set, and that actually allows us to decouple, to have an additive dependence on the field size. Great. So I think I'm gonna. I want to thank you very much again for listening and for the opportunity of speaking here. Thank you.
You can just pick up those microphones. Should be able to pick it up or you can use this microphone. Comments, solutions to conjecture. Okay, thank you so much.
Thank you.
So we have about 10, 15 minutes till next talk.